I'm Sherri Shulman. I teach at the Evergreen State College. Format of this slide set is introduction. I'm going to go over type classes, algebraic data types, functors, applicative functors, and continuations in asynchronous behavior. I actually teach programming language design. So although I do teach C and C++, and Haskell and other languages. Mostly I'm interested in how different ideas from different languages are implemented in other languages, but more generally how the ideas behind those type features or language features spur creativity and designs and language evolution in other languages. So really, programming languages are not just about implementations, they're also about ideas. And before you can actually do a solution, you have to have an idea about how you want to frame the solution. So even looking at patterns and design patterns and features in other languages can inform how you program in C++. Right. Okay, so why Haskell? I'm a Haskell fan. I actually didn't put one of the things I really like about Haskell in here. Haskell's lazy. So I don't know if how much people know about Haskell. I didn't put that in here. But Haskell is statically typed. It's strongly typed. It's referentially transparent, which means it has no side effects, which I also say down there. So wherever you execute or compute with a Haskell function, you will get the same value. Remember, side effect means that something is happening outside of the main purpose of the function, so that you're altering state in some way that may alter the running behavior later. It has first-class functions, which means that functions are values, just like other values. We have a certain set of operations that we can do on functions. So not all operations are meaningful for all data values or data types. But so I can't add functions, but I can compose them, I can apply them, I can do a variety of things, including partial application. And those of you who use the STL, C++ has introduced the equivalent of partial application by using the bind operator in the STL. My opinion is that partial application is a great idea, and bind is a very clumsy implementation of partial application. Haskell has a very expressive type language. The more expressive your type language is, the more things you can type statically and get essentially compile time errors for fairly sophisticated expressions. So although I don't cover it in this talk, think about what it might be if you could have a type that would express that, let's say you're doing a zip on lists. If you had a type that would allow you to express that the two lengths of the two lists need to be the same. You don't care how big the lists are, but they need to be the same length list. If you have that available in the type, then in fact you can get a type error rather than a dynamic runtime check on how long the lengths of the lists are. Those are something called dependent types, which I'm not covering today. It has very orthogonal language features, which means that the different features in the language don't impact other features that are unrelated. So I'm old enough so that I remember when C++ was first being defined, there was a very active blog on all the things that nobody could figure out what exactly they meant. So that it's such a complex language, or at least initially, that there were many expressions that were semantically unclear. And part of the evolution of C++ was, of course, actually pinning those things down. That really hasn't happened in Haskell. It has a very, very clear definition, clear semantics, no side effects. All right, so how does this impact C++? C++ is a very different language than Haskell. The language features and design patterns in Haskell can promote ideas about how to structure solutions. So you can think of Haskell as being a design language and C++ the implementation language. And as a matter of fact, Haskell has been called an executable specification language. I just want to say, just so I don't sound like I'm totally an academic, I did work for 10 years at Bell Labs, and I worked on the Unix operating system. By the way, I brought my own laptop running Ubuntu, and nobody could figure out how to get my laptop to talk to the AV machine, so I have a borrowed laptop. All right, support for C++ concepts. So I read a paper describing C++ concepts, which I really like. And there is a beta version of GNU's C++ concepts, which they did not have for my platform, and I would have to remake the entire thing from sources, and I did not have time in my agenda to get to that. But I really think it's a really seductive kind of addition to C++, really adds to its expressivity. Now, unfortunately, I am really bad at pronouncing names, so I don't know how to pronounce his name, although I have read many of his blogs and papers. Bartos? Anyway, I read his blog and looked at some of his Haskell patterns and how he is implementing them in C++. So there's really a lot of interest in moving some of these features in and out. And the original format of this paper, I actually had many different languages. So because I teach programming language design and I teach a wide variety of languages, I looked at how a number of new languages are doing the same kind of thing. So looking at Scala, if anybody has taken time to look at that, or Rust, there's another language called Go. All of these are really taking the same kind of ideas and focusing on different ways to put them together. All right, this is sort of a typo heading. It's just there from my typesetting. All right, so if we look at some Haskell features that we're going to look at, type classes. The easiest way to think of type classes are it's like an interface or a pure abstract class. It really specifies constraints on a type. Okay. Algebraic data types in two forms, functors, monads, and continuations. These are really all in support of a certain kind of genericity, because the goal is to provide enough language features so that you can create solutions or schema that capture a broad set of solutions. So really Haskell promotes a lot of reuse, and it promotes it in a way, of course, that's not object-oriented, so you're not necessarily reusing code in the same kind of way as you reuse code via inheritance. What you're reusing is a type structure, so that you fold things in to this type structure. And has anybody here used things like a map, fold? Those are higher order functions. And if you have access to these higher order functions, you can often put together really quick solutions to relatively challenging or abstract problems by using the right kind of components in your fold and your map and so on. All right, so what is a type class and how does it support genericity? How does it differ from interfaces or abstract classes? Does it have inheritance? Does it have default definitions, dependencies? How does it support genericity? All right, so this is an example. By the way, all of my examples, I have citations and references and links to the papers at the end of this talk. So once it goes up, you'll be able to get to the original sources on all of these. So this is an example of a hash set implemented as a set of type classes and implementations. So, and it actually has an implementation using concepts, which I couldn't test, but was derived from this paper. Not this paper, the paper I read for the authors. So we can say that we're going to introduce a type synonym called list of x. LIST is a new name that we're giving this type, and in fact, it's just a list of x. X is a type variable, so a list can hold elements of any type. We're going to introduce a class. Something that has empty means it has the function empty. Can everybody read this type notation here? Okay, does anybody have any questions about it? So : is the indicator in Haskell that something has that type. In case you don't know, Haskell we don't use explicit type tags in Haskell. So in a type class, you have to explicitly say the type of something because you're not giving a definition. But in general, when you give a definition in Haskell, it infers the type. Right? And there are some moves in C++ to provide that as well with decal type and decal val. I'm not sure if that's actually in any of the C++ compilers now or if it's still at the experimental stage. All right, so empty is a function that takes an x and returns a bool. Clearly here, x is a type it will be a type. It's a type variable. If something has empty, it will have declared the function empty. The intent here, of course, is X must be some kind of container type. All right, but in general, of course, we're only giving the type, not the semantics. X is hashable, so the class hashable, we say X is hashable if it contains a hash function. And again, that's a typo. Sorry about that. Hash should be returning an int, not a bool. It would not be a very interesting hash function if it returned a bool. You know, some typos you just can't find. Okay, over here is an example of a context. All right, so down here, assuming that X has an empty and that element X, which is a type, is hashable, then X is also a hash set. All right, and this is just a declaration down here, type element X. It's a little bit like a prototype in C++ or the times in C++ where you have to declare that a qualified type is in fact a type. So this has the same role here. We're telling Haskell that element X is a type, unspecified, so that we're able to say size has the type X arrow int. You can tell here that the semantics of this, X has to, again, be a container type. Size, since we're talking about a hash, size is telling how many elements are actually in the hash table. Okay. Everybody okay so far? All right. Now, we're going to say, okay, int is hashable. Notice here it correctly is returning an int. So this is just a stub kind of hash function. So the easiest hash function you have, if it's an int, you can just return the int. We can say that int map has an empty, so int map is provided in the Haskell prologue in the module data. All right, so it gives you a mapping function. All right, and it has a null function itself. All right, so I'm just going to say that empty is data.intmap.null. All right, now hash again. We have another context here. If k is hashable, then an int map of list of k's is a hash set. Okay, everybody okay with this? So a list of k, remember, was just a list containing elements of type k. We're going to treat the list of k as an int map. And that's the elements that we have in our hash set. And here, this is just an alias, so here on after, we'll just refer to it as k. And down here, we give our definition for size, and we'll just use the size defined in the int map module. All right, this isn't a very clever hash set. I mean, we didn't give it a very clever hash function, but it's serviceable. And here we can actually specify it. I didn't put in the definition for almost full. In fact, one of the other things about Haskell is we have infinite lists. So because we have infinite lists, almost full is sort of meaningless. So that in the implementation, it's just a stub. So we start out by creating the empty set. So the empty set is just an empty list. And that's what null is. And then we can test it and say almost full. So the reason we can have infinite lists is because Haskell's a lazy language. So the only thing you need to know for a particular list is how to get the next value, right? Which is a really nice feature because some things you just don't have to worry about. All right, so there are the three classes we spoke about. We restrict the types X that model hash set to those types X that model has empty and hashable. This data type, the data type int map list k, is still not a concrete type since k is a type parameter. But so long as k models hashable, we're type correct. And it's all we need for an element in our hash table or a hash set is that it be hashable. And actually, we have two constructions then. We have both the container that holds the k. It has to have certain properties. And we have the values that are held inside the k. It has to have a certain property. The example we did instantiated k with int, resulting in a full implementation. But k could be instantiated with any type with the appropriate constraint with full type safety. Okay, so that's the goal here, of course, is that you want an expressive enough type system so that you can put in all the constraints that matter for your implementation. And you also want to be told of any errors up front. All right, so that we don't want to actually have errors occur at runtime. Unfortunately, we haven't gotten rid of all runtime errors yet, but working on it. All right, so this is the C++-like implementation using concepts. And it's pretty parallel to the Haskell implementation by design. There's another typo there. So a hash set given a type name, parameterizing a type name x is an extension of hasEmpty. So we assume that we have a hasEmpty, which I didn't define here. And then we introduce hash set. And element is a type name. Here we're going to give the requires. So it's an extension of hasEmpty, but it's going to require that element itself be hashable. So that represented the two different constraints we had, one on the container and one on the element in the container. And we'll have an int size. And then we have our hash set itself with an int map. It's going to be a list of k, and again, we're going to just instantiate our int map with a particular list of k. Okay, never mind. I'm not sure why I chose the letter M. I don't think I used M before. I tried to keep this. Oh, I guess I did, size M. All right, so that's just the argument to the size. All right, everybody okay on this? So we've got some of the same kind of characteristics in the concept implementation of a hash set as we had in the Haskell. It's a little wordier. In general, C++ is wordier than Haskell. But this particular implementation, I think, is fairly clean otherwise. All right, we can talk about our almost full here. Again, there's the only algorithm that we've discussed, and I didn't give the definition, but the instantiation here would be, okay, I have my H will be my hash set, and then my test will be almost full. These should be the same case, lowercase for uppercase. So hash set is subclass of hasEmpty with an independent constraint that element be hashable. Exactly the same, really, as the Haskell one. The two implementations and their semantics are parallel. As I was saying, concepts are not yet a part of standard C++ implementations, although I hope they will be soon. They provide an explicit type-level constraint that serves both to explicitly communicate requirements and also provide static information. So actually, those are two pieces. I'm always telling my students that actually, your code is often read by other people. Actually, it's read by many people. It's written by you, the programmer. It's written by everybody that's in your team. Whoever inherits your code and maintains it is constantly reading your code. So one of the main purposes of a program is, in fact, to be a method of communication. So the more information you have in your program for people who are reading it, the better. I did come from this Unix environment. There was one of our members of the team who used to say, never commented anything, and the reason he never commented anything was his comment was, no comments don't lie. So the worst thing that you can do is have a comment in your code that is incorrect relative to the code. And one of the nice things about typing information is a kind of comment. It says something about correct use, but it's checked by the compiler, so it never can lie. So if you have a type in there, it is correct. Type classes do not have code inheritance. Although the context constraints enforce an inheritance of type expectations. So we're not getting inheritance of code, but of course when we have those constraints, so if we go back over here, this constraint, this context, hasEmpty x, hash table element of x, says that x has to meet those constraints. That's inherited. The constraints are inherited via these context constraints. And if x has an empty, if it satisfies hasEmpty, then it has the method empty. If it satisfies hashable, then it has the method or function hash. All right. So that even though you're not inheriting the code, you're inheriting the interface. All right, then where did I get up to? All right, you should always be suspect when anybody says clearly. So my claim is they clearly support genericity. They support genericity because I put in the necessary constraints on the types that can instantiate K. I've guaranteed that that in any implementation, whatever K I provide will be checked, so that therefore I can use it for a variety of hashable things. Reusability, because once I have a hash set, I can write anything using the hash set regardless of what kind of items the hash set includes. And their ability to construct hash maps from a variety of types, assuming the types meet required capability. It's a checkable predicate, prevents instantiations for which the implementation would not make sense. Okay. All right, so is everybody okay on this? So we looked at type classes. I think this is a good example. We're going to move on. I'm moving up the abstraction ladder. So the next one we're going to get to is algebraic data types. So what's an algebraic data type? How does it differ from classes and subclasses? What are the advantages? How does it support genericity and reusability? I'm going to use actually two examples, or two related examples, but they're mostly based on an evaluator. I mean, because we're in language design, everybody uses evaluators. Everybody know what the lambda calculus is? I should ask, does anybody not know what the lambda calculus is? You have to ask both the positive and the negative way. Okay, I'm going to give a definition shortly. Haskell is based on the lambda calculus, but probably the most famous language that everybody has heard something of, even if not used, is Lisp. So most people have heard of Lisp as well. There's a whole family of lambda calculus languages. So there's Haskell, there's Lisp, there's Scheme, there's ML, and there's other lesser-known ones. They all are organized on the idea of functions and applications. So functions are abstractions, applications are applying an abstraction to some other term. Now, algebraic data types are also called discriminated unions. And although I define this here, I'll talk about this later. We're also going to talk about something called generalized algebraic data types, which are an extension. So suppose we do want to implement a lambda calculus language untyped. We might do this directly using an algebraic data type, also known as a discriminated union. We'll say that a term in the lambda calculus is either a variable or an abstraction, or it's an application. Right? If you notice over here, the VAR and the ABS and the APP are called constructors. They're not constructors like C++. They're really value injectors. In other words, constructors in C++ and in Java do make a new value of the indicated class, or a new instance of the indicated class. So if I have a class and I have a constructor, when I execute the constructor, in combination with the compiler and the operating system, I allocate all of the memory required in order for me to have an instance of that type, and I return either a reference or the type or the value itself. So in some sense, you're doing the same thing. You're creating a new value of an indicated type. And as a matter of fact, one of my professors from long ago used to call classes an instance factory. All right, so you can think of every single time you call a constructor, you're making a new instance. These differ a little bit because although ultimately they are like functions, they're really like tags. And that's why it's called a discriminated union. You can, if you don't think of I know C++ is immersed in memory allocation and storage requirements and all sorts of things that are intimately related with the machine. The lambda calculus is not. It was introduced as a very abstract language. And one of the most common ways of understanding Haskell is not associated with the machine at all, but it's associated with a term rewriting system. So you can think of yourself as being at a really abstract level without having to think about the underlying hardware. So this says var, abs, and apt are like tags. They live with the values that are produced. So if you think of this just as the text representing itself. And a variable will represent as a string, or could have represented as a character. And an abstraction, we can abstract on a variable or a string, and then the term represents the body. So an abstraction is a function. If you notice over here, all functions take exactly one argument because I only abstracted on one string. All right? But the term itself can be, yet again, another abstraction. so that essentially you get the equivalent of a multi-argument function by having a sequence of one-argument functions. Does this make sense to everybody? I don't have a board, so I'm really impaired. Alyssa, who is my student, will tell you that I'm constantly jumping up to write things on the board. Now instead I just have to wave my hands. All right, so and then application is given a term, I can apply it to another term. Function application in the lambda calculus is actually modeled by beta reduction and substitution, but we're not concerned with that now. If I did this in C++, usually the standard way of doing this is with classes and subclasses. All right, so that I can say that term is the top of my inheritance hierarchy, and whatever behaviors I didn't give any here. And then I can say that a var is a subclass of term, and what it adds is it has a string for its name, and ABS, the abstraction, is a subclass of term, and it has the variable. In other words, what it's going to abstract on, and it has the body, which is a term. And an application is a subclass of term, and it has the L-func. So the L just refers to the left-hand side. So the function on the left-hand side is just like LHS and RHS, right? That we use when we're talking about L vowels and R vowels. And then the argument, that's a bad name, but the other term is really the term that we're applying it to. It may be anything as well. So notice there's no constraints here. Terms they're not typed. There's no way in which we say what's meaningful, what's not meaningful. Anything that is computable, we can compute in the lambda calculus, including we can compute some things that are not computable. We can attempt to compute something that is not computable. We can put together something that will not terminate, that has no meaning. One of the things, the reason it's called a discriminated union is because if you think about the way this is presented, I have three kinds of things, and I could think of these as sets. And I'm saying a term is really the union of all these sets. So it's the union of all possible variables, all possible abstractions, and all possible applications. All right. But usually when you do a union, where the original thing came from disappears. So if I do a union of two sets of integers, I don't know where the integers came from afterwards. I just have now a larger set of integers, assuming I have a homogeneous set. So what happens in a discriminated union, because the tag still exists and it is tagged with the value, I always know where that object, that value came from. All right. So when I write functions using an algebraic data type, I'm going to have to give the criteria, or what the action of the function should be for each one of those discriminated elements. All right. So this is not, the style in Haskell is actually to give a distinct rule for each case. All right. So this is one function, eval, and the three different cases are for the three different kinds of values that we have. So if I want to eval a variable, if I want to evaluate an abstraction, or I want to evaluate an application. I didn't put in the right-hand sides on this because, in fact, to fully do it, I'd have to put in a store and a few other things to make it a full evaluator. All right. Now, the C++ implementation uses classes and subclasses. Each of the kinds of term is implemented in a subclass. So in order to implement an evaluator, I'm going to split the evaluator among the different subclasses. All right, so the subclass for a variable will have its own eval. The subclass for an application will have its own eval. And the subclass for an abstraction will have its own eval. All right. All right, so how do the two approaches compare? So we may want to do some changes. So let's sort of think about how they compare when you're actually modifying your code. So that there's two kinds of ways that we might want to modify the code. One is we might want to add a new kind of term, right? And the other one is we might want to add a new kind of behavior. So far, all I've said is that the only behavior we had is eval, and I gave the three kinds of terms that we have. So what if I decide that I want a new kind of term? Let's say I want to have a constant. All right, so I could extend my term. So now a term is a variable, or it's an abstraction, or it's an application, or it's a constant. I know cons often is used for lists, but in this case, cons means constant. And now my evaluator, I'll have to add a new rule for what to do for the cons element in a term. All right. That doesn't seem so bad, but what if I had a lot of different behaviors? So I only had a val, but what if I had a lot of different behaviors? I'll have to add this new rule for each one of those behaviors. Right? So there's this measure of how well organized one's code is by determining how many things you have to touch if you make any changes. And the more things you have to touch if you make changes, or the more fragile your code is in some way. Every single time you touch something and fix or extend one thing, you introduce another bug or another need someplace else. So there's a desire to limit the number of changes that need to be made to really essential. And the better your code is designed, the more you've restricted where the changes arise. So this is one place where you might say, well, that's a little bit of a weakness because I've added one kind of term, and now I've proliferated a lot of changes that need to head to all the behaviors. Granted, there's only one behavior in this. In C++, if we add the new subclass cons, all right, then I only have one kind of constant in this one, an int. All we'll have to do is add a new eval function. You could say that this is better in that sense because I only ended up having to change the thing I just added. All right, instead of this ripple effect where I had to change a bunch of different function definitions, I only have to change the subclass that I just added to my hierarchy. Everybody okay with that? All right, what if we want to add a behavior? So the flip side is I'm happy with my terms, but I want to have a new behavior. So what if I want to have a pretty printer? If I want to add it in the algebraic data type design, then all I'll have to do is add that function. So there's the pretty printer, and I have to give all the different cases for each element of the discriminated union, but I don't have to touch anything else. All the other methods, the val and any other behaviors that I have, are not touched or not altered. On the other hand, in the OOP design, we're going to have to go and touch every single subclass, even though none of those subclasses changed, in order to add the new behavior. Okay. So this is sometimes called the row versus column problem. In other words, you don't get anything for free. If you change something, either you're changing something in the row or you're changing something in the column. So if you think of the elements of your discriminated union as being one of the axes and the behavior as the other one, either I'm going to have to change a row or I'm going to have to change a column. I've always thought that kind of example really demonstrated that these are really comparable. One's not better than the other. They're just different. So I'm not pushing this on Haskell, but it would be really nice if we could get some of the features of a discriminated union into C++. The desired features are, one, the ability to enumerate the possible allowable values or types in an object-oriented program. All right, so right now what happens, of course, that you don't really know what all the subclasses are of a particular class. Not only that, not only do you not know who are the direct descendants, like the term has an abs, an app, a term, a constant, a var, and so on, but you also don't even know how deep the hierarchy goes. So you don't know how many refinements there are on any one path. So that makes it, sometimes it makes it hard. So for instance, there are a lot of times when you really want to know that two things are in fact actual instances of the same class. There are times when, like if you think of binary predicates like equality, I really want to know that two things are both elements of the same class. There are some times that I really want to know all the different direct subclasses because I want to make sure I have full coverage. So that's something that we could do if we had discriminated unions. And we also want to allow for the ability to use user-defined behaviors for all possible types. Or get a compile time error. So that's in reference to the fact that the original way of dealing with this, in fact, was an enum type. Enums have been around forever. So you use an enum type in a union. So this should make it clear sort of what discriminated unions or algebraic data types do for you. So I'll make a struct, and I'll have an enum type that says all the different kinds of values that can be held in this structure. Enum types require that you use primitive types in the list, and this one clearly doesn't have primitive types. If you notice here, there's an abuse of the enum type to make it similar to the above example. And then you have a union, and inside the union you have all of the different possibilities delineated. Now, anytime you have to do something with this union, or this discriminated union that we're constructing, you have three things that you have to make coherent. One is you have to make sure that the enum tag has the correct value relative to the data that you actually stored, and any function or behavior that is using this has to correctly preserve these. So if you think of doing a get or a set, anytime you do a get, you have to make sure that you check the tag appropriately and then access the correct field. So if the tag says that it's an abs, then you're going to look at the abs field. If a tag says it's an app, then you're going to look at the app field. And then when you do a set, when you assign to it, you have to make sure that you assign it correctly. This is very error prone. It's been around since C, and it certainly has had a lot of uses, but all of the responsibility for doing this correctly is on the shoulders of the programmer, and there is no static type checking that can prevent you from making an error. Right? Because the compiler doesn't know that these things are related. To the compiler, they're all separate components. So I already said this. Any function wanting to implement a behavior would have to inspect the type tag, get the appropriate field, and so on. Don't get any help from the type checker. So there is a more expressive approach that is proposed by Alexandrescu. That I can create a type list. The type list actually allows you to use user-defined types, and it's kind of variant record. Right? I think variant records were introduced in Pascal, so it's an old idea. All right. But this is at the level now of the type checker. All right, so now the type checker has a definition for what a type list is. So every single time you access the variant with its associated type list, the type checker can ensure that these things are in sync. The details of the implementation are beyond the scope of this presentation, but the paper is really interesting. I really recommend it. So a variant must include constructors that accept any type in the type list, so I should be able to make an element of the variant with any one of those types. I need to have an overloaded assignment for each one of the types that also is type correct, a safe way to convert to any of the types in the type list. All right, so that because C++ has a significant amount of type coercion that happens automatically, I want to make sure that if I'm storing into a variant, that I have a means to convert it appropriately. The way, I haven't used this term before, but in the C++ literature, the way that they talk about, for lack of a better term, I can call pattern matching. If you notice in our definition of the eval, I had those type tags, and that's really, we usually refer to that as pattern matching. But you can also think of it as what's called decoherence. In other words, how do you break down a type? A way to determine the actual type stored in the variant, a way to convert a coercive value appropriately, and I don't know if this is the hardest, but it never comes up in Haskell because it's below the level of the programmer control, a way to determine storage needs. So now this is different values of different types have different storage requirements, including alignment. A union only allocates enough storage to hold the largest of the elements that it may hold. So you have to make sure that you're aligned correctly in terms of word, half word, quad word, or whatever boundaries, and as well that you've allocated enough space for the largest element that will be held in your variant. Now, although it's not required in order to do this, having pattern matching would be a real plus. This has to do with how easy is it to actually do the decoherence. How easy is it for you to specify what the kind of object is? And you certainly don't want this to be a type check at runtime. You'd like the type information to be handled statically, even if there is going to be some component that may happen at runtime if you have a pointer that is actually producing a dynamically created value to check whether, in fact, it's appropriate to that variant. All right, everybody okay with this? By the way, all these papers have references at the end, and also the citations. So. Now, unfortunately, although this does a lot for us, it doesn't do everything. All right, so I happen to really like this example. It's called the generalized algebraic data type. This is a term language. It's no longer the lambda calculus. It's a little term language. This term language is it's just for pedagogic purposes. So a term can be a literal integer, or it can be a successor of a term. It can be a predicate check, is it 0? It can be an if term, term, term. And it can be a pair. Now, notice I have to use term because, in fact, I can't say that suc always applies just to an integer because, in fact, I could apply suc to a successor term. So I should be able to apply successor to successor of, successor of, successor of 0. All right, so I can't get any extra type information here. And that has definitely unintended consequences. So first of all, there's two kinds of values here. I have both Booleans and integers. All right, the result of is 0 term should be a Boolean, and the result of successor of term should be an int. The result of an if term, 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 well, it could be anything. It could be either a Boolean or an int, or in this case, a pair as well, because I introduced a pair. Once I have a pair, I can, in fact, have an infinite number of items here. I could have a pair of literal literals, or I could have a pair of literal. So I can keep on building this up. So I have a fair amount of variation for such a simple language. Now, the problem is that I can't actually write an evaluator for this particular algebraic data type, because if I think of an evaluator as returning a value in a particular value domain, I've got 3 different value domains specified here: integers, booleans, and pairs. All right. And the pair domain or value domain is actually a sequence of value domains. So I have an infinite number of value domains here. But even if we just look at Boolean and integer, I can't write an evaluator for it because there is no connection between Booleans and integers. So the type for the evaluator has to produce one result type. Boolean and integer just aren't it. All right. So the usual way is to introduce yet again another algebraic data type. So here's the 2 cases to highlight it. So if I evaluate is 0, that's clearly going to return a Boolean. And if I evaluate successor, that's going to return an integer. And this will not type. Okay. However, I can, in fact, introduce another domain, a value domain, and in it I'll say, here's all the different ways that I can produce a value. And you can think of this as a wrapper type. So again, it's a discriminated union. Now my evaluator is going to produce a val. Now, it's not perfect because now anytime you use a wrapper type, you're constantly having to wrap and unwrap it. So every single time I want to do something, I want to evaluate it, I produce a value. If I actually want to see it, I have to unwrap it. And every single time I want to do any computation with it, I have to unwrap it, do the computation, and then wrap it up again. So there's a certain inconvenience in using that kind of intermediate domain. But more serious than that is this particular example here, this term. This term is type correct according to what Haskell knows about this language. All right, Haskell doesn't know that suc needs to apply to an int, ultimately, because I didn't give it that constraint. All right, it doesn't know that that the first term after the int, after the if, has to be a Boolean, because I didn't give it that kind of constraint. All right, and as a matter of fact, I can't give it that kind of constraint in regular algebraic data types. All right, so we have to go to a generalized algebraic data type. So here's the same language written as a generalized algebraic data type. This, by the way, is not standard Haskell. So this relies on an extension to Haskell. The reason it's not standard Haskell is the type checker is no longer guaranteed to terminate. All right. If you don't have type annotations. All right, remember I said that Haskell does not require explicit type annotations, so the culture in Haskell is very much that the type checker is going to draw all the inferences from the information that you provide in your program. If you don't give type annotations, these generalized algebraic data types no longer are guaranteed to terminate. A type checker that doesn't terminate isn't very useful. It's not the style to give type annotations, but I'm going to live with it because I want to get this kind of flexibility. So now I get to put in a bunch of constraints. So literal has to take an integer, and it gives me a term int. Notice now what happens over here is I've embedded the kind of value that is returned, and I've put in constraints where appropriate. So a successor needs to take a term int, and it takes a term int. Is 0 takes a term int and returns a term bool. If takes a term bool, that's the expression, then a term of any kind A and a term of any kind of A and returns a term A. And a pair takes a term A and a term B and returns a term AB. Pair is a little unusual because I introduced an unqualified type variable B, which wasn't mentioned in the header. But this one solves the problem. All right, so now at the cost of putting in type annotations, I've actually gotten a much more expressive eval. I no longer have to have a value algebraic data type because now all the information is right here and the evaluator knows what kind of thing is going to be returned. And it's going to return something that is a parameterized value. Okay. Well, my slides are a little bit too full, sorry. All right, so algebraic data types and object-oriented programming. As I was saying, the advantages and disadvantages aren't necessarily as clear as you might want or think. Algebraic data types have more precision. There's no need to consider subtype polymorphism. We don't have to query what type an object actually is. It's there in the type. Algebraic data types can enforce that each function covers all cases and inform the programmer about any missed cases statically. So if you write your function and you miss one of the cases in your discriminated union, you get static type checking, and that's one of the things you're informed about. On the other hand, algebraic data types are less dynamic. We have to consider all the values that may occur, right? Since I have to a priori decide all the things because every single function I write is going to have to give a rule for every one of the elements in the discriminated union. Adding new values is easier in a subclass hierarchy, as we were talking about, potentially at increased cost and adding behavior. But generalized algebraic data types add to the expressivity of the type system and allow more information to be captured in the type so that more type errors can be detected statically. So although this is being explored in the object-oriented world, there are a variety of really interesting ideas out there. So again, it's a paper to keep on top of. All right, so now we're going to move from algebraic data types to functors. Right. So Haskell functors capture the idea that something is mappable. A mappable thing is a generalization really of the map function over lists with the type. So here's the type of a map function. It takes a function of the type A arrow B, and it takes a list of A's, and it produces a list of B's. A functor is something that defines a mapping function. Only we're going to generalize it. It doesn't have to be for lists. It could be for anything. It's the same thing as our hashable or a hash set. To some extent, we're not concerned with the semantics here, although some semantics do come out. But we're mostly concerned with the kind of behaviors that are provided in the same way as abstract classes do. So here we can say that something is a functor if it gives us an F map. And F is the name, is a parameter. It's, although often F stand for functions, here it's standing for a functor. So if F is a functor, then there is an F map defined that works on these functors. It expects to get a regular function, not a wrapped function, and then a functor that holds an A and a functor, and it returns a functor that holds a B. Now, we're being really fuzzy about this. You could think of functors as containers. They hold some value. But you could also think of functors as holding a computation. In Haskell, often the difference is irrelevant because functions are values. So if I say that a functor holds a value, I'm not really committing to what kind of value it's holding. It could hold a function, or it could hold, for instance, another functor for that matter. It could hold anything. All right, so you can think very generally of a functor as something that holds a value and provides a mapping function. A list happens to be an instance of a functor. So I'd have to say that, of course, instance in Haskell is similar to implements in Java. Okay. So I can say that a list, that's a notation for a list, is a functor, is an instance of a functor, and I'll define it, the F map, to be the lists map. Okay. Here's a common type in Haskell that embodies the idea that a computation may fail. So maybe type holds an A if the computation succeeded, but if the computation failed, it holds nothing. Right. And maybe is a functor. So in order for maybe to be a functor, I have to give the definition of its F map. So if I F map F applied to something, just something, something that evaluated to an actual value, is just that just something with the function applied to its contents. And if I apply it to nothing, then we get back nothing. So the way of looking at this, by the way, is maybe types are strict. What that means is any time a computation produces nothing, nothing percolates through the entire computation. So far, functors don't seem to do much other than create a uniform way to look at a lot of things, anything that can be mapped. So lists can be mapped, trees can be mapped, pairs can be mapped. We already saw that even something so little as a maybe type, which holds just one thing, can be mapped. There's a limitation here. We expect the functor to take one argument. If you notice, when we talked about it, our functor only took one argument, their FA. So I have to specify, a functor can only, what I specialize a functor to is something that can be described in one argument. All right. We can use partial application to bridge this constraint. I'm actually going to talk a little bit about, well, I'm not going to get to everything because I have too many things. Do people know, I've already talked about partial application, so who here is familiar with partial application and who is not? So how about currying and uncurrying? And who is not? There's no value judgment here associated. All right, so we're going to use partial application. The idea behind partial application, suppose I have a function of two arguments, or what I think of as two arguments. But remember, when we saw the lambda calculus, all functions really have one argument, but what they return may be another function. All right. So that idea is intimately related. Every single time I want to reduce essentially the arity of a function, I can just apply it to one more argument. Eventually, you'll get to the point where you have no more arguments to apply it to, and then you have an irreducible or normal form term. Okay. So if we have a function of more than one argument, we'll have to apply it to enough arguments so that we have a function of one argument in order to be able to use it with a functor. All right. One advantage of this uniform way to look at mappable things is that we can compose them or combine them because we know they have a uniform structure. And this is the same thing we've done for a lot of things, like the hash set relied on the fact that we knew everything that was supported by the elements that go into the hash set, and we know what the container supports, so therefore we can use it in a variety of applications just relying on that contract. So we can do it with some things that may seem a little unusual. So the arrow type is just a constructor for a function. In other words, I normally think of arrow really as being the type of a function. So a function from a list to an int, the length function, I would write down as list of a arrow int. And there's the arrow in there. But an arrow is also a constructor for this it is a constructor for this type. So I can think of arrow applied to R. It's put in the prefix form. Normally arrow is infix. In Haskell, when you wrap it in parens, you're essentially changing its orientation from infix to prefix. You can go from prefix to infix as well. So this says that I have a function that takes an R. All right. I've already reduced the arity then by 1. All right. And now, because I'm looking at something that's going to return some other value, this represents all the functions that take an R, and then they're going to return something else. So they fit the model of a functor. Okay? We're really talking about them really generally. So a function type is R arrow B for arbitrary types R and B. If we partially apply the type to the first argument, we get a constructor of one argument, as required for functors. So arrow char is the type of a function that takes a char to a value of some other type. Arrow int is the type of a function that takes an int to a value of some other type. So it's a functor. What's the definition of it as a functor? So I had to say what to do when I do an fmap. All right, so I really like this example. So if I fmap f and g, so fmap applied to f, applied to g, I'm going to return, remember I have to return something that's in the functor. In this case, the functor is an arrow. So I'm creating an arrow type. There's the lambda x, that's what I abstract on. And there's the arrow, and that's giving us the rest of the body. I already know now that g is a function. So I can't write here. But if you remember, the type of fmap is it takes a function from a to b, and it takes something that is a functor, in this case an arrow r, because that's what we said we had. So therefore I know that g is an arrow r. Does that mean I have to stop and ask for questions? All right, I'll finish this, and then I'll stop. I'll flip all the way to the end, and then I'll take any questions. And then what I'll do is, okay, I'm going to apply the g to an x. Now I know that this x must be of type r. Does anybody know why it must be of type r?
Because it's declared so in the top instance.
Right. This said that the functor I'm looking at is something that takes r's. All right. So g takes an r. And x, and I'm returning something that takes an r. Since I'm returning something that takes an r, x is an r. All right. G gets applied to the r and returns an a. F is a function from a to b. So this is returning me an arrow r that returns a b. Okay. All right. So that is really clever. But look, what is that? If I look at this, this is just composition. All right, so I could have just as easily have said fmap is just function composition. All right, so Alyssa tells me that we don't have any time left. The end. I talk really fast, but obviously not fast enough. So here's all my citations. So there's where all the examples came from. And following that are all of the papers. And here are online links to all of the papers and blogs. So you can look up all of the information. Does anybody have any questions?
One thing you mentioned, particularly early on in the talk, was the use of Haskell as a design language and then C++ as an implementation language. Yeah. Do you know of any tools that might be able to take either Haskell or a subset of Haskell
and do an automatic conversion from Haskell to C++?
Yes.
You know, there was one at one time, but I don't know what happened with the development. Yeah, so I don't know of any current ones, but that's really an interesting question.
Do you remember the name of the...
I can find out if
okay.
you give me...
I'll talk to you after the
Okay.
talk.
Yeah, Haskell used to be, at one point, used to be known as something called an executable specification, because it's much more abstract. I don't have to think about any memory allocation. I don't have a lot of the issues that surround what we think of as more conventionally designed implementation languages. I don't have to worry about what kind of calling protocol I'm using, or call by value, call by reference. Are things constant or not constant? It's all value-based. There is no state. There are a lot of things that make it very nice as a specification language and abstract away all these details. But of course, a lot is happening in the compiler, you know, so that, and if you really want an efficient implementation for something, Haskell may not be the best way to go. But it has a lot of really appealing features. Anything else? All right, well, thanks very much for coming. I'll have these things out.